All right, I'm going to work through my notebook for this database prediction hackathon. First, I import the standard libraries, NumPy and Pandas for data handling, Skited NER for splitting and matrix, Matplotlib for plot, and ChargeBoost for the model. Then I load two Excel files, the train Excel and the test Excel. I print the shapes just to confirm the data loaded correctly. The training set includes the label database binary, and the test set includes an ID column for submissions. And next is some quick EDA. I check the column names and data types, and I also count missing values in train and test. Then I look at the target distribution using value counts and a bar chart. This is important because the dataset is class imbalanced. There are more zeros than ones. Since the computation uses F1 score, not accuracy, this imbalance matters a lot and it shapes the rest of my modeling decisions. And after that, I check the duplicate rows in the training data. If duplicates exist, I drop them using drop duplicates. The reason is simple. Duplicates can make the model look better than it really is during validation. And they can also increase noise. Removing them usually makes training more stable. Uh, After that, now I separate features and labels, set X to all columns except the target, and Y to database that binary. For the test set, I drop the ID column because the model should only see features. Then I split the training data into train and validation sites using train test split with stratify y equal y. Stratification is important here because it keeps the positive rate roughly the same in both splits. So validation results are more reliable on imbalanced data. In this cell, I compute a correlation matrix across the feature columns and visualize it as a heat map. The goal isn't to remove features here, since we only have 21 features and tree-based models handle correlated inputs reasonably well. But it helped me understand the struggle of the dataset and spot highly correlated feature groups that might matter for interpretation later. And here's the mean model. I use a ChargeBoost classifier, which is a guaranteed boosting ensemble of decision trees. To handle class imbalance, I compute scale pulse weight as the number of negatives divided by the number of positives in the training split. That makes the model pay more attention to the mandatory class during training, which usually improves recall and often improves F1 as well. Then I fill the model on the training split and generate validation probabilities. I start by evaluating with the default threshold of 0.5 and print the mean matrix F1 precision, recall accuracy, and rock awk. Because the leaderboard matrix is F1, the classification threshold is a big deal. So instead of fixing it at 0.5, I run the symbol threshold search. I sweep thresholds from 0.05 to 0.95, compute F1 at each threshold. Compute F1 at each threshold on the validation site and select the threshold that gives the best F1. Then I plot F1 versus threshold so you can visually see where the model performs the best. This rank step is basically converting probability scores into final class predictions in the way that best match the evaluation matrix. And now that I have the best threshold, I generate final validation predictions and compute the confusion matrix. From the matrix, I extract TP, TN, FP, and FN. This is important because it tells me how the model is making errors, not just the overall score. Then I reprint the matrix using the tuned threshold. Finally, I add a quick cost interpretation in a health screening context. False negatives missing someone who actually has database risk, and they are usually more costly than false positives, which typically just lead to extra follow-up. Next, I look at feature importance from XGBoost. I create a table of feature importances and plot the top 15. This gives me a basic interpretability layer. It tells me which variables the model relied on most to celebrate database risk versus no database. It's also useful for guiding future feature engineering or discussion in the write-up. In this cell, I show dimensionality reduction example using PCA. I standardized the features and then feed PCA to retain 95% of the variance. I print the original dimension and reduce the dimension. For this baseline, I'm not actually feeding PCA into the model because tree-based models like XGBoost don't necessarily benefit from PCA. I included it mainly to show the concept and to connect it to the lecture topics. Finally, I just retain the same XGBoost setup on the full training dataset to maximize the data used for learning. Then I predict probabilities on the test side and apply the best threshold I found earlier to convert probabilities into 0 and 1 predictions. I create the submission data frame with the required format, ID and database binary, and save it as the submission CSV. This field is what I upload to the computation. So overall, this notebook follows a stable pipeline, quick EDA, clean duplications, handle class imbalance, train an ensemble model, optimize the threshold specifically for F1, and then generate a clean submission. Thank you, that's all.